Welcome back to The Explainer. Today, we're diving into a groundbreaking research paper that totally challenges everything we thought we knew about how smart AI really is at mathematics. We're going to look at some fascinating new research that finally gives us a way to peek under the hood. We want to know, are our most advanced AI models actually thinking, or are they just really good at pretending to?
So let's start with a provocative question for you. When an AI model gives you the perfectly correct final answer to a complex math problem, did it actually reason through all those intricate steps to get there? Or did it just memorize a clever shortcut? As AI gets more and more powerful, figuring out this distinction is becoming absolutely crucial. I mean, are we building brilliant digital mathematicians or just incredibly sophisticated guessing machines?
The researchers behind this recent KDD paper really hit the nail on the head here. They point out that if we want AI to help us with real scientific progress, like proving new theorems or discovering new physics, we have to grade its step-by-step reasoning, not just its final answer. They make a super compelling case that the way we currently test AI is fundamentally flawed, and well, they've built a brand new system to fix it. Here's our roadmap for today's explainer. We'll be hitting 1. Grading AI's math homework, 2. The mask-proof pipeline, 3. Making proof self-contained, 4. Hiding the key step, 5. Testing the top AI models, and finally, 6. The future of AI math. All right, let's jump right into Section 1, Grading AI's math homework. Think about how we currently test these models. Old benchmarks like GSM-8K or math basically give an AI an A+ just for getting the final number right at the bottom of the page. But true mathematics? That requires certified proofs. You have to show your work. If an AI just spits out the number 42 without a rigorous formula-level derivation, it's kind of useless for real scientific discovery. But grading full natural language proofs usually requires a team of expert human mathematicians, which is, as you can imagine, incredibly expensive and impossible to scale. Which brings us to Section 2, the mask-proof pipeline. So, how do we fix this without hiring an army of math professors? Enter the mask-proof pipeline. It's this automated system that essentially creates a strict fill-in-the-blank test out of real, high-level math. Here's how it works. First, paper collection. It mines fresh research papers directly from archive. Second, self-contained recovery. It fixes any missing context in the text. And third, agenic masking. It deliberately hides a crucial mathematical step. The AI then has to prove its worth by correctly filling in that exact blank. Just look at how this whole journey flows. It starts on the far left with those messy, raw LaTeX files pulled straight from archive. Then it moves through an automated curation phase where the context is fixed and the mask is applied. Until finally on the right, boom, you've got a verifiable benchmark that's tested by a specialized LLM judge. It's a completely automated, scalable loop that transforms real-world research into a precise evaluation tool.
Let's zoom in on that second step in Section 3, making proofs self-contained.
You can't fairly test an AI on a proof if half the required definitions are sitting in a totally different document, right? It's like asking someone to finish a puzzle, but hiding half the pieces in another box. So, the pipeline uses an agent to hunt down all these missing dependencies, like external lemmas or cross-references, using Codex TLI and pulls them directly into the text. It agentically grabs all those missing pieces to make the problem completely self-contained, giving the AI everything it needs to solve it right there on the page.
And to really hammer home why this matters, the researchers tested AI models on math problems without this recovered context. The result? A massive performance drop of 11 to 23%. That is a huge hit. It just goes to show you, you literally can't measure an AI's true reasoning ability if you're secretly starving it of the background information it needs to make that logical leap.
All right, moving on to Section 4, hiding the key step.
Look at the sheer leap in complexity here. On the left, you've got a standard competition math problem, the kind older benchmarks rely on. But on the right, that is a terrifyingly complex, research-level matrix equation pulled straight from a published paper. The mask-proof pipeline takes that matrix and literally slaps a mask tag over a crucial part of it. The AI is now forced to reconstruct that exact matrix step from scratch. No multiple choice, no easy outs.
But wait, there's a catch. You can't just black out any random step. The researchers actually discovered that if you randomly hide steps, AI can easily shortcut its way to the answer. For basic bookkeeping steps, AI guesses the missing piece 90% of the time just by glancing at the surrounding text. Even algebraic manipulation gets shortcutted almost 78% of the time. That is exactly why the pipeline uses AI agents to specifically target the absolute hardest, most vital inference steps, like applying a lemma or a theorem, where guessing simply won't work.
Here is the big takeaway from this part. Random masking makes standard models look way smarter than they actually are, artificially inflating their scores by over 40%. It lets them skate by on shallow pattern matching. This agentic masking, however, acts as the ultimate AI lie detector. It strips away all the easy context cues and completely exposes models that can't perform deep multi-step reasoning.
Now you might be wondering, who grades the grader? How do we know the AI gave the right answer for the missing blank? Well, the team built a specialized automated evaluator called Mask Proof Judge. And get this, it achieved a staggering 96.8% agreement rate with actual human mathematical experts. We finally have an automated grader that's basically as reliable as a math professor, but can grade thousands of complex proofs in seconds.
So, how did the big players actually do? Section 5. Testing the top AI models. This is where things get wild. There is a stark, undeniable divide in today's AI landscape. When tested on these research-level masked proofs, reasoning-enhanced models, the ones that actually generate an internal chain of thought before answering, performed incredibly well. We're talking GPT 5.2 high scoring up to 63.3% and DeepSeek v3.2 thinking hitting nearly 50%. But the standard models, the ones that just try to output the answer directly, they absolutely collapsed. Look at Qwen 3.0b, scoring a measly 8.1%.
Notice that hard boundary right at 32%. Every single standard model fell below that line, while almost every reasoning-enhanced model soared right above it. This proves beyond a shadow of a doubt that models generating internal chains of thought aren't just slightly better. They are operating on a completely different planet when it comes to mathematical comprehension. Test-time reasoning is for sure the undisputed key to unlocking higher-level math.
Finally, let's wrap up with Section 6, the future of AI math.
The impact of this pipeline is honestly a total game changer. First, it replaces all that costly, unscalable human expert grading, letting us evaluate AI instantly. Second, it gives us faithful, reproducible step-by-step measurements, not just final answers. And third, this is a big one, it fiercely resists data contamination by mining only fresh, unreleased archive papers from August to October 2025. Meaning, there is absolutely no way the models could have just memorized the answers during training. It's a true test of on-the-fly intelligence.
So as we close out today's explainer, I'll leave you with this final thought. Based on that staggering 32% performance gap we just saw, is the era of simply asking an AI for a final answer completely over? Are we now permanently entering an age where AI absolutely must internally show its work and reason step by step to be of any use in scientific discovery? The data certainly points that way. Thanks for joining me as we explored the mask-proof pipeline. Keep exploring, keep questioning, and I'll catch you on the next explainer.